Hi, so this is going to be a quick recap of lesson 3 on October the 31st. So we're just going to, like in class, we're going to go over the questions that we did here. I can't remember whether I talked about the four things that can happen when light strikes an object, so I'm just going to verbally. So usually the light that surrounds us is white light that comes out from our lamps, that comes from the sun, so which is comprised of all the 7 colors. And when it hits an object, it can either be reflected, which means the light bounces off the object. It is either absorbed by the object, in which case the object appears dark or black in color. It can be refracted, which is a word that we learned maybe today, which means light passing through the object. And we drew a diagram on it, but it basically means light just goes straight through. So, for example, a lens, light goes straight through a window or water or a contact lens or some things like that. It can also, and we also talked about how most substances do a combination of these. So there's not just one thing that they do. So water reflects some of the light, but it also refracts some of the light passes through the water. Similarly, most objects partially absorb some of the light and reflect some of the light, and this is what leads to different colors being formed. When, for example, if you take the example of a leaf, white light strikes the surface of the leaf, and the leaf absorbs all the colors of light except for green. So all the colors of white light except for green. So violet, indigo, blue, yellow, orange, red, the leaf has absorbed, and it only reflects green color light, or the wavelengths of light that are green in color. When those wavelengths hit our eyes, we see the leaf as green. Or in the autumn, some chemicals in the leaf change so that they reflect different colors of light, so we see the leaves as orange or yellow in different seasons. So we're going to continue straight ahead into this worksheet. Okay. How is energy related to frequency? Energy is directly proportional to frequency, which means as frequency increases, energy increases, and vice versa as well. So gamma rays, which have high frequency, also have high energy. Radio waves, which have low frequency, also have low energy. In contrast, directly proportional to an inversely proportional, which is frequency and wavelength. Right, as one increases, the other decreases. How are disturbances in the electromagnetic field caused? They are caused by movement of electrons, and this is how electromagnetic waves are produced. So in an X-ray production machine or in your microwave at home, in the microwave, for example, there's a device called a magnetron, which moves electrons in a circle, and this movement of electrons causes a disturbance, which causes the wave, like we talked about. Convert following to scientific form. So I'm going to put the decimal place after the first non-zero number. How many times did I move it? 1, 2, 3, 4, 5, 6. So times 10 to the power of -6 because it's a small number. Decimal after the first non-zero number. So we'll note that the decimal for this is naturally here. So I want to move it to over here. That's where I want it to be. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 times. I'm going to put a positive 8 up there because it's a big number, so I need to multiply by 10. Here I'm dividing by 10 in this part A. Here the answer is 5.8 times 10 to the power of 1. Expand, so we're going 9, 1, and then 4 zeros because I just added a bunch of zeros after the 9.1, and then I multiplied by 10 5 times. That's what the exponent 5 means. So I'm multiplying by 10 5 times as I'm moving the decimal place to the right 5 times. So 1, 2, 3, 4, 5. Decimal place goes there, which means 4 zeros. If 10 has a negative exponent, that means I'm dividing by 10 4 times, which means I'm going to I don't have space. Do something like that. decimals here, moving to the left 4 times, 3, 4. So that's 0.30289. And again, 10 to the power of positive 8. So I'm multiplying by 10 8 times. So I'm going to move this decimal. So add a bunch of zeros after, just so that you can move the decimal place and actually move it 8 times, which I believe is 86, followed by 4 more zeros, hopefully. Okay. Question 5 is kind of an obvious question. I mean, in general, what are the invisible parts of this EM spectrum? Is basically all of the spectrum except visible light, right? So visible light was the only visible part of the spectrum. Everything else is invisible. So I briefly mentioned at the beginning what color is. Color is just a particular wavelength of light, or wavelength or frequency or energy, right? It's just a particular kind of wavelength or frequency or energy of light. Just continue. A black object is an object that absorbs all the light that is shown on it. And we looked in class about Vantablack, which is the blackest object in the world. It absorbs almost 99% or 98% of all light that shines on it, which makes it really, really appear to be just like a hole. Most normal day-to-day objects also reflect some of the light, so we can see them as kind of like a grayish color. They're not completely black, right? These two questions we didn't go over in class, so I will make it part of my next video. How do we see color? Do objects have a specific color? And we talked about this at the beginning as well. Color is just some objects absorb some colors of white light and reflect others, and the ones that are reflected are the colors that we see to be the colors of those particular objects. All right? Okay, so now we're going to quickly define or describe different kinds of light production very briefly. We have incandescence, which is light produced from a hot object like the sun or the old style of lamps, where a tungsten filament is present and you pass electricity through that. It heats up, and that heat produces light, or it also gives off light. The important thing to note is these are very inefficient because most of the energy is converted into infrared radiation, that's heat radiation, and only some of it is converted into visible light. Alternatives to incandescence are light-emitting diodes, or LEDs, like computer screens. These use semiconductors, which are silicon-based with a little bit of boron or phosphorus added into them, and this causes electricity to flow in only one direction, which makes them produce light, basically. That's the movement of electrons that's producing the light in there. We talked about chemiluminescence, which is light produced due to a chemical reaction such as glow sticks. It's also called as cold light because it does not produce heat. We talked about bioluminescence, which is a chemical reaction but occurring in a living body such as a plant or animal, usually catalyzed or using enzymes such as luciferase was the enzyme present in fireflies that helped them glow. We also talked about the two important ones, fluorescence. And we looked at the X-Men movie where somebody was absorbing energy and then releasing it. So fluorescence is basically where you absorb, or materials, not you, absorb UV light and then release some energy. So UV light has higher energy than visible light. We remember that from our little spectrum that we talked about at the beginning. So it absorbs UV light of a higher energy and releases visible light, but it releases it all at once. So it doesn't glow for a very long time after it has absorbed the light. It's absorbing and quickly releases it. The last important one, we have to talk about fluorescent lamps. Those use fluorescent, but they're more efficient and more cheaper than incandescent lamps, but they use mercury, which makes them a disposal hazard. It's difficult to dispose of them, and you have to be very careful around them. Sorry, back to phosphorescence. This is the exact same principle as fluorescence, right? So it still absorbs UV light, releases visible light, but it releases it slowly over time. And these materials are usually phosphor compounds, so they're called phosphors. They contain phosphorus, right? And these are the ones that absorb UV light but release it slowly over time, like glow-in-the-dark stars and stuff like that. And that's called phosphorescence. We also talked very briefly about triboluminescence, which is the light created by striking two rocks together, which we also said was, as for the moment at least, pretty not useful for, humans in general. I guess, actually, I don't know if it's the same rocks that, Stone Age people used to strike fire. I'm starting to wonder about that, but because that probably would have been a useful, kind of thing to the invention of fire and all. But the textbook said that apparently this doesn't have any practical applications, so that's that. I'm sorry I'm 2 minutes over my own allotted time. These videos are getting longer by the day, so I apologize. And yeah, hopefully this was useful. All right, see you guys in class.